It's almost dizzying how quickly things evolve, isn't it? The technology just keeps accelerating, and keeping up with how it impacts our world, especially fields like design, can feel like a monumental task.
Yeah, absolutely.
That's exactly why we created the deep dive. We're here to try and cut through some of that information overload, specifically for you, someone intrigued by the powerful connection between, data and design.
And today, we're taking a close look at a couple of lectures. They're titled 2025 Data in Design Class 01, Lecture B, Data and Design Code for Design, Parts 1 and 2.
Right.
Our goal really is to extract the essential insights about data, its growing role in design, and maybe why developing what's called computational thinking is becoming, well, increasingly vital.
Okay, let's kick things off with maybe a quick thought experiment about the future. Remember back in, say, 2008,
Vaguely, yeah.
there was this online chatter about a hypothetical phone, bigger screen, could play videos, had music. Sounds completely normal now, right?
Totally standard.
But at the time, a lot of people were really skeptical. Comments were like, YouTube on a phone, really? Wondering if a 4-inch screen even qualified as a phone.
Huh. Yeah, I remember that skepticism.
Then, boom, the iPhone arrived and just fundamentally changed everything.
Well, what's fascinating there is just the speed at which our perceptions can shift and like how unreliable simply extrapolating current trends can be sometimes.
Definitely.
That example really highlights the potential for those aha moments, when we start to understand the underlying forces at play.
Right.
Instead of just getting caught up in predicting the next fleeting gadget, the lectures suggest a more robust approach maybe to future-proofing our knowledge.
Which is it?
Focusing on what won't change. It's kind of like designing based on the laws of physics. Those aren't likely to be rewritten anytime soon.
That's a great way to put it. Speaking of fundamental shifts, the lectures touch on how knowledge creation itself seems to be evolving.
Oh, yeah. How so?
Well, the romantic image of the solitary genius in their lab might be giving way to something more collaborative, almost unseen, particularly in fields like computer science.
Interesting.
And this leads to a really intriguing question posed in the lecture. What is the most expensive product in history?
Oh, okay. That's a thinker. What's the argument?
The lecturer makes a compelling case that it might not be a physical object at all, but rather something intangible, like, say, the Google search engine or the vast infrastructure powering Amazon's website.
Ah, okay. I see where this is going. Not something you can hold.
Exactly. These aren't things you can, hold in your hand, but they are massive, interconnected networks driven by data, reaching billions daily. Their impact is almost immeasurable.
That's the analogy they used, right?
Yeah.
About the car.
Yeah, we don't have a generic concept of car just floating around. We only have specific models like a sedan or an SUV.
Right.
The abstract product of a search engine only exists in its continuous operation and, well, the sheer volume of data it handles.
And if we connect this to the bigger picture for you, listening, someone interested in design, think about it. A few lines of code can now deliver services to a global audience.
It's kind of mind-blowing.
Yeah. The underlying data and the infrastructure that supports it become incredibly valuable. It represents this massive collective intellectual effort.
So how do we, as learners and designers, navigate this rapidly evolving future? The lectures bring in a really insightful idea from Jeff Bezos.
Okay.
Instead of constantly trying to predict what will change in the next 10 or 20 years, focus on asking what will not change.
The unchanging fundamentals again.
Exactly. For you, this is a powerful lens for directing your learning towards enduring principles and skills.
And this focus on, well, unchanging fundamentals stands in stark contrast to a lot of traditional education, doesn't it? Which often emphasizes just memorization of facts.
Right. The lectures wisely quote Richard Feynman on this.
Oh, what's the quote?
Don't memorize, understand the principle.
Simple but powerful, yeah.
Absolutely. The lecture argues that while rote memorization might have had its place maybe in the 20th century, the 22nd century demands a different set of skills.
Like what?
Deep understanding, robust problem-solving abilities, sharp critical thinking. This really connects, I think, with your desire to gain thorough knowledge without feeling overwhelmed by just a mountain of isolated facts. It's about grasping those core foundational ideas.
Yeah, that makes a lot of sense.
Yeah.
And this shift in what's valued is also a key driver behind what we've seen called the coding boom.
Right. Everyone talking about learning to code.
But the lectures are careful to point out that the real goal isn't just about being able to type lines of code, it's more about cultivating computational thinking,
Computational thinking.
which is really a fundamental and broadly applicable problem-solving skill.
We've heard prominent figures like Barack Obama, Mark Zuckerberg, Anshul Su all emphasize the importance of coding. But as the lectures clarify, it's not just about mastering a specific programming language, right?
Yeah.
It's about developing that computational mindset, that structured, logical way of breaking down problems and developing solutions.
Exactly. And this crucial intersection of data and design isn't confined to just one area. The lectures briefly touch upon the wide range of scales and domains where it's becoming essential.
Right.
From massive geographic information systems, managing environmental data, down to the minute details of architectural design, product development, and even incredibly complex simulations. It's everywhere.
Okay, so for us visual thinkers, how do we actually take real-world objects, abstract concepts, and get them into a computer in a way we can manipulate and analyze them?
Right, the translation problem. The lectures explain two fundamental methods: vector and raster data.
Vector and raster. Okay.
What's fascinating is how these two different data formats essentially remember spatial information.
Yeah.
Vector data, as the lectures illustrate with the polygon example.
Like drawing with points.
Yeah, exactly. It uses a series of precise points with X and Y coordinates to define shapes. It's a very efficient and accurate way to store geometric information.
Think of it like connecting the crucial dots to define the outline of something. Simple enough.
Mm,
And raster data takes a fundamentally different approach, right?
exactly. Raster data divides a given space into a regular grid of small cells, or pixels.
Okay, like a digital photo.
Precisely. Each of these pixels is then assigned a specific value, such as a color in an image. This creates a two-dimensional matrix, basically a grid of information. Imagine a mosaic where each tile holds a single color, and together they form a picture.
So both vector and raster methods serve as a bridge, taking the tangible real world and translating it into the digital world in a format that a computer can understand and, well, process.
Right. And the lectures really encourage us to expand our thinking about vectors beyond just their strict mathematical definition.
Yes.
They can be incredibly powerful tools for imagination within the digital realm. For example, simply defining 4 coordinate points lets you instantly create a rectangle in your design software.
Okay, yeah.
Then, more advanced mathematical operations like dot and cross products become even more sophisticated tools in your creative toolkit.
That makes intuitive sense. I mean, a single data point, like 3, 2, doesn't convey much on its own, right?
Not really, no.
But when you project it onto a coordinate system, say with a horizontal x-axis and a vertical y-axis, it suddenly gains meaning. It represents a specific location in space.
Exactly. It's
Yeah.
all about having that shared framework for interpretation.
Like a common language.
Precisely. And this framework is often implicitly built into the tools we use. CAD systems, computer-aided design, for instance, naturally guide us towards thinking about designs in terms of three-dimensional XYZ coordinates.
Right. It just assumes that.
Yeah. And beyond these basic coordinates, there's a wealth of other geometric data that design software captures. Things like UV points that define locations on curved surfaces, information about the curvature of those surfaces, and control points that define the shape of complex NURBS curves.
NURBS curves, those are the smooth mathematical ones, right?
Yeah, exactly. Used everywhere, computer graphics and design for very smooth, precise shapes.
It's interesting how seemingly distinct data types can actually be related. The lectures mention that raster data, those individual pixels, can even be interpreted as vectors sometimes.
Yeah, under certain circumstances. It really highlights that the way you encode and then decode the data determines its meaning and how you can actually use it.
This is a crucial point about data, isn't it? And how different systems interact.
Absolutely. A design file saved in one specific software format might be completely unreadable by another program without the correct input-output protocols, the I/O protocols, to translate the underlying data structure.
So the software needs to speak the right data language.
Exactly. The software acts as a data processor, and it needs to understand the specific language and organization of the data it's given.
So having a solid understanding of how this spatial data is structured is absolutely key if you want to manipulate it computationally, especially with complex design challenges.
Definitely. And the lectures introduce 3 fundamental data structures that are essential for translating design concepts into a computational format: graphs, pixels, and voxels.
Graphs, pixels, and voxels. Okay.
What's particularly insightful is how each of these structures organizes data and represents relationships in different ways.
Yeah.
We've already talked about pixels for 2D raster data.
Right.
And voxels basically extend that concept into 3 dimensions, like 3D pixels.
Got it.
Graphs, on the other hand, can be thought of as another type of vector entity, maybe, but instead of just defining shapes, they focus on the connections of relationships between different elements.
So which one you use depends on the problem.
Pretty much. The choice of which structure to use really depends on the specific problem you're trying to solve or the type of real-world information you're working with.
The lectures then go deeper into the idea of relationships within pixel data. It's not just a collection of individual colored squares, right?
Not at all. Each pixel essentially knows about the pixel surrounding its neighbors.
Okay, so they're aware of each other.
This awareness of adjacency between pixels is incredibly powerful. It allows for all sorts of spatial analyses, like identifying every area on a map that falls within a certain distance of a river.
Oh, right, like a buffer zone.
Exactly. Or determining which buildings have good access to public transportation based on the proximity of relevant pixels. These kinds of computations rely directly on understanding the spatial relationships between the data points.
That's a really practical application. And the game of life example they mentioned.
Ah, yeah, Conway's Game of Life.
That's such a compelling illustration of how applying very simple rules to these neighboring pixels can lead to incredibly complex and, emergent patterns.
It really is. It shows how local interactions at the data level can generate surprising global behaviors from the bottom up.
So cool.
Exactly. And consider a 2-dimensional height map, where each pixel represents a specific elevation.
Like a topographic map made of pixels.
Pretty much. The lectures explain how this raster data can be used to reconstruct a fully 3-dimensional model of the terrain.
Wow.
And once you have that 3D model as data, you can then extract even more valuable information, like the steepness of the slope at any given point, for further analysis in your design process.
The lectures also describe an example where interacting with a single data point on a map causes a color gradient to change around it. This isn't just a visual trick, is it?
No, it can actually represent real-world dynamics. Think about something like crime data.
Okay.
A criminal act in one specific location doesn't exist in isolation, right? It can influence the perceived safety and potentially even the actual crime rates in the surrounding neighborhood.
Ah, so the gradient shows that ripple effect.
Precisely. That color gradient visually represents this kind of influence spreading outwards. The lectures even touch on research exploring how data interpolation techniques and real-world interventions, like increasing police presence or investing in local revitalization, can potentially influence these data-driven outcomes.
Interesting. We also get a brief look at the classic bin packing problem.
Ah, yes. Fitting things into boxes efficiently.
Another straightforward example of the kinds of logistical challenges that can be tackled computationally, trying to fit a collection of items of different sizes into a limited number of containers.
And then we have voxels, which are essentially the 3-dimensional equivalent of pixels.
The 3D pixels, right?
Each voxel represents a tiny volume of space and can contain various types of data. Visualizing data within these voxel grids, for example, using the size of a sphere within each voxel to represent cost, can be a really effective tool for problem solving in 3D design scenarios.
So you can visually identify high-cost areas to avoid.
Exactly. It allows you to intuitively identify and avoid areas with high costs or other constraints.
The lectures then make an important distinction between continuous data, like those pixel maps where values can smoothly transition,
They're like gradients.
and discrete data, like the distinct elements and connections in graphs. What's the fundamental difference for us to understand?
Well, continuous data flows without clear breaks, like that gradient of color blending seamlessly. Discrete data, on the other hand, is made up of separate individual components.
Okay.
The lectures highlight that graphs are fundamental to how mesh data structures are organized in 3D modeling. And they're even used behind the scenes in BIM software building information modeling, like Revit,
How so in Revit?
to define the relationships between different building components. For example, how a specific wall is connected to a particular floor slab, or which door belongs to which room. It tracks all those connections.
So it's all about understanding the connections.
Exactly. And the lectures emphasize that many seemingly disparate problems can actually be addressed using these underlying graph structures, including representing hierarchical relationships, like the organizational structure of a school with its departments and grade levels.
And you can apply rules to these graphs.
What's really powerful is that you can apply rules and logic to these graph structures to simulate dynamic processes. The lectures describe an example where elements within a graph were programmed to exert a repulsive force on each other to prevent them from overlapping.
Ah, like the map labels example, maybe?
Similar principle, yeah. The underlying data within the graph records these interactions, allowing you to visualize how the system evolves and settles over time.
And this relates back to the idea that in design, we're not always searching for a single perfect best solution, right?
Exactly, but rather exploring a range of optimal solutions based on various environmental factors and constraints. Finding good fits, not just one answer.
And the recurring emphasis on understanding pixel and voxel data really drives home their importance. Why are these two so fundamental in computational design?
Because they provide a foundational way to represent and analyze spatial information in a discrete, computable format. Whether you're analyzing environmental conditions using pixels on a geographic map or understanding the complexities of 3D space with voxels,
Right.
these structures allow us to bring the intricate details of the real world into a digital environment where they can be analyzed, manipulated, and ultimately inform our design decisions.
The lectures also touch upon the fact that the level of computational design expertise among architects and designers isn't a simple yes or no question, it's more of a spectrum.
Precisely. It ranges from a basic level of proficiency in using software like Rhino and Grasshopper, where you're primarily interacting with pre-built tools,
Okay, using the tools.
all the way to the ability to write custom scripts to automate tasks, then further to creating entirely new data structures tailored to specific problems.
Getting more advanced?
And finally, to the advanced utilization of graph, pixel, and voxel structures for maximum flexibility and problem-solving power. It's a progression.
To really illustrate this in practice, the lectures present a compelling example of a site analysis project. How does integrating diverse data play a role there?
In this example, various layers of real-world data, things like the existing topography represented as slope, the amount of sunlight exposure across the site, visual sight lines, and proximity to amenities are all integrated into a computational model.
So you layer all that info together.
Right. This allows for the simulation of how people might move through the site based on these factors, providing valuable insights to inform the design of buildings and spaces. You can predict movement patterns.
Wow, okay. We also see an interesting project focused on automatically arranging text labels on a map. That sounds like a deceptively complex problem.
It can be, yeah. The core challenge is positioning numerous labels so they clearly identify their features without overlapping and obscuring each other.
How does computation help solve it?
The lectures describe using a collision detection and repulsion algorithm. The system identifies when labels are too close and then iteratively moves them apart until a clear, non-overlapping arrangement is achieved.
Ah, so it pushes them away from each other.
Exactly. This beautifully illustrates those fundamental computational concepts, identifying relationships, in this case, spatial proximity, and then applying rules to manage those relationships.
And for simulating more dynamic things like air or water movement, the lectures introduce vector fields.
Yeah, vector fields. Fundamental in fields like CFD, computational fluid dynamics. They're created by defining a direction and a magnitude, or strength, at numerous points throughout a space.
Like a field of little arrows pointing the way.
Exactly like that. Each arrow indicates the direction and force at that location. Then, when you introduce virtual particles into this field, their movement is determined by the vector where they currently are.
So simple rules create complex flow.
Precisely. By applying these relatively simple rules at each point, you can computationally simulate incredibly complex phenomena, like wind flow around a building or water movement in a river.
So the first part of the lectures really sets the stage by emphasizing this core idea, taking the often intuitive design process and formalizing it, using structured data pixels, voxels, graphs to represent space, and building computational systems on top.
Yeah, laying the foundation.
Now, let's transition to the second part, the outro of the lectures, where the focus shifts slightly but crucially to the thinking that underpins all of this.
That's right. While understanding these data structures is absolutely essential, equally important is the way we approach problem solving using these tools. This brings us to the core concept of computational thinking.
Okay, computational thinking.
The lectures break it down into 4 key components: abstraction, decomposition, pattern recognition, and algorithm design.
Abstraction, decomposition, pattern recognition, algorithm design. Okay, let's unpack those a bit. The lectures use a really helpful and slightly humorous example, trying to get an AI robot to make a banana milkshake.
Yeah, the milkshake robot.
It illustrates the difference between high-level human instructions and the incredibly detailed low-level instructions a computer needs.
Well, what's so insightful about that milkshake example is how much implicit knowledge we humans just take for granted. A simple instruction like, make a banana milkshake,
Yeah.
glosses over a huge number of individual, very specific actions.
Like what?
Reach for the banana, grasp it correctly, peel it, add milk, operate the blender, pour the shake. For a computer, each of these seemingly obvious steps needs to be explicitly defined in a precise sequence.
Oh.
This really highlights the level of abstraction that we humans naturally perform in our thinking and communication, but it needs to be made completely explicit when we're writing code for a machine.
So at its heart, coding is essentially translating our often vague, high-level design intentions into a series of these very precise, unambiguous, low-level instructions that a computer can then execute.
Exactly. The lectures further clarify this by contrasting high-level versus low-level communication.
Okay.
Think about giving feedback like, do better. That's high-level, open to interpretation.
Right. Not very helpful sometimes.
Compare that to giving specific instructions. Adjust posture, focus attention, take detailed notes. That's low-level, precise, less room for ambiguity. Coding operates at this low level of precision.
And the lectures make the important point that while we humans naturally communicate high level, this can lead to information loss or misinterpretation when we try to translate complex design processes into code.
Yeah, that need for clarity and explicitness is paramount.
This distinction provides a good segue into contrasting two broad approaches to codifying design processes: traditional rule-based programming, or Software 1.0, and data-driven machine learning Software 2.0.
Right. Software 1.0 is characterized as being more linear, based on direct cause and effect. The lectures use a simple example. Hit someone, they feel pain. Direct, predictable consequence from a rule.
Okay, cause leads to effect.
In contrast, Software 2.0, machine learning, often involves inferring potential causes from observed effects. For example, someone is in pain. A model might analyze lots of data to infer likely causes.
So working backwards from the effect.
Kind of. It relates to the difference between deductive reasoning software 1.0 following rules and inductive reasoning software 2.0 learning patterns from data. And crucially, machine learning relies heavily on vast amounts of data.
Now, the lectures introduce a mathematical concept that's crucial for machine learning: linear algebra. Why is that so fundamental here?
Because at its core, machine learning is about finding patterns and relationships in data. And to do that effectively, you need a way to represent data spatially.
Spatially.
Yeah, the lectures use large language models, LLMs like ChatGPT as an example. In these models, words are encoded as high-dimensional vectors in a mathematical space.
So words become points in space.
Essentially, yes. This vector representation allows the model to mathematically calculate relationships between words, similarity, frequency of co-occurrence, things like that.
So by representing data in this kind of multidimensional space, you can then do math on it, like group things.
Exactly. You can perform operations like drawing lines or planes to group similar data points, that's classification, or fitting curves to predict trends, that's regression. Placing data in space enables these operations.
Got it. The lectures also briefly mention generative AI and critical AI.
Yeah, just quickly. Generative AI can create new data, like images or text. Critical AI focuses more on analyzing and evaluating existing data and systems.
But the really empowering message here, for you listening, is that even if you don't plan on becoming an ML expert,
Right.
understanding these fundamental computational concepts gives you a powerful new lens, a way to think about how you can approach and solve design problems computationally.
It's similar to learning 3D modeling software, maybe. Once you grasp the basic tools and how they function, you can start to imagine and create increasingly complex forms. It unlocks possibilities.
And the lectures mention resources available in both Korean and English for digging deeper into computational thinking and design.
Yep, helpful pointers for further learning.
So when we have a design challenge, how do we practically start applying this computational thinking process? What are the steps?
The lectures outline a logical sequence. It begins with clearly identifying the problem or issue you want to address. Could even be the initial design concept itself.
Okay, know the problem.
Then, crucially, thoroughly understanding the problem in all its nuances, and importantly, defining the specific inputs you'll work with and the desired outputs you're aiming for. That input-output definition is absolutely essential for any computational approach.
Can't skip that.
No. The lectures also highlight the importance of simplifying breaking down complex problems into smaller, more manageable parts. Decomposition.
The lectures then touch on some interesting ideas about designing algorithms, like you can't always control the whole and the parts simultaneously.
Right, that idea that sometimes you need to focus your control on specific parts or aspects at a given time in a complex system. You can't micromanage everything at once effectively.
And the difference between deterministic and stochastic algorithms.
Yeah, significant distinction. Deterministic algorithms follow a strict, predictable set of rules, like a multiplication table, always the same answer.
Okay.
Stochastic algorithms incorporate some element of randomness or exploration, like a mouse finding cheese in a maze by smell, exploring promising paths rather than exhaustively checking every single one.
Exploring versus exhaustive search. Makes sense.
The lectures also connect the growing importance of data to the rise of data science, describing it as this powerful intersection of domain knowledge, computer science skills, and statistics.
And this leads to the concept of design science as a parallel field.
Exactly. Design science essentially integrates established design principles with computer science methods and the analytical power of data.
And there are lots of related terms.
Yeah, the lectures list several often overlapping terms: computational design, AI-driven design, AI-aided design, machine learning-aided design, design engineering, all emphasizing the role of data and computation for rapid iteration and analysis in design.
We then see a really helpful diagram in the lectures contrasting traditional design methods with those incorporating computation and data.
Yeah, visually showing the difference,
Yeah.
highlighting the iterative loops and analytical power you gain with the computational approach.
The core message that keeps coming through is the fundamental importance of codifying the design process, making the implicit steps explicit so a computer can work with them.
Absolutely. And ultimately, the lecture suggests that design itself is essentially a process of decision-making among numerous possibilities. Computation helps navigate that landscape.
For listeners keen to dive deeper, the lectures mention a past academic paper and some articles in architectural publications.
hmm Further reading suggestions. And mention of collaborative research projects applying these methods, like with Seoul National University.
To further illustrate practical applications, the lectures showcase a diverse range of examples, computational techniques applied to different challenges.
Yeah, things like sophisticated data processing, advanced image segmentation, detailed structural analysis. What's insightful is seeing how seemingly different applications often share fundamental underlying computational principles and data structures, like graphs or pixels being used in varied ways.
The lectures also make a point that even something like color is significant data with defined color spaces for computational work.
Right, and another tool discussed is network analysis, using graph structures, which can be applied directly to analyzing building designs, circulation, space relationships, etc.
And there are Grasshopper examples and English course materials for that.
Yes, resources mentioned for exploring network analysis further.
We then see a fascinating structural analysis example. Computational agents, like columns, iteratively finding optimal positions.
Yeah, supporting a ceiling under load. It really demonstrates how data structures and agent-based systems can tackle complex engineering problems dynamically. The agents search for good solutions.
What's interesting there is the interplay between the agent's deterministic behavior, like minimizing stress,
Right, their programmed goal.
and the influence of real-world constraints, like human paths or fixed areas where columns can't go.
Exactly. It highlights how computational solutions can incorporate and respond to complex, real-world conditions, not just operate in a vacuum.
The lectures also briefly describe a thesis project using Grasshopper for environmental analysis, agent-based landscape growth, and even interaction in mixed reality.
Yeah, it sounds very cutting edge. Integrating analysis, simulation, and interaction in one interface.
Another insightful example simulates resource management trees, timber, a factory.
Right, showing interconnected relationships. How actions in one part of the system affect others. Helps understand consequences of decisions.
And for finding optimal solutions in complex environments, reinforcement learning is mentioned.
Briefly, yeah, as a technique for training models based on rewards and penalties in an environment. Learning through trial and error, essentially.
Bridging digital geometry to physical reality, the lectures mention tools compilers for fabrication tasks, like unfolding complex shapes.
Tools that automate the translation from 3D model to flat patterns for cutting and assembly. We also see an example modeling material expansion from sunlight using graph-based spring models to simulate physical behavior.
There's a quick glimpse of robotic fabrication too, which underscores the point that software fundamentally is data processing, often just addition.
Yeah, leading to that thought-provoking question. Given this basic operation, where does the creativity truly lie in software engineering versus traditional design?
Hmm. The lectures then move through a rapid-fire succession of other computational design applications, giving a sense of the breadth of its potential impact.
Which naturally leads to the crucial question for you listening.
Ah,
How do you actually begin to learn computational design?
and the immediate recommendation is
Start by thoroughly exploring the provided video resources. Watch the lectures.
in terms of specific programming languages, Python, C Sharp, and TypeScript are mentioned as relevant. How does someone starting out choose?
Well, the lectures rightly point out it often depends on the projects you're interested in. Web stuff, JavaScript, TypeScript is key, Windows apps, C# is common.
And Python.
Python's great for data processing, scripting, integrating with lots of software. It's very versatile and widely used, often embedded in design tools like Grasshopper.
But the underlying concepts are more important than the specific language initially.
Exactly. Understanding variables, data types, operations, control, flow, the logic and structure that's truly important, regardless of the first language you pick. The lectures strongly encourage reviewing materials on these fundamentals.
What about math? Does it come up?
The topic often does, yeah. The lectures offer a helpful perspective. While strong math helps, what's perhaps more crucial initially is mathematical thinking.
Mathematical thinking.
Using math concepts to explain phenomena, understanding vectors, spatial relationships, even with just basic operations like addition, multiplication, thinking spatially and logically using math concepts.
Another really key concept introduced is APIs, application programming interfaces. What are they and why are they important for designers using code?
Think of an API as a well-defined way for software pieces to talk to each other. It exposes certain functions without revealing all the complex underlying details.
Like a restaurant menu.
Exactly like a menu.
Okay.
You can order specific dishes, use functions, without needing to know how the chef prepares them. For designers using code, understanding and using APIs is often a primary goal. It lets you leverage powerful pre-built tools like getting weather data without writing everything from scratch.
So recapping the learning journey. Focus on programming fundamentals, geometry principles, discretization, pixels, voxels, choosing computational approaches, software 1.0 versus 2.0, and applying optimizing systems.
Right, and remembering that core design data types like curves, surfaces, meshes are often based on graph-like structures.
The lectures also point towards educational resources and a Q&A collection.
Yep, valuable starting points for further exploration. The overarching message is encouragement, continuous effort, learning through doing, even through mistakes.
There's a relatable anecdote shared about the time it initially takes to solve coding problems.
Yeah, emphasizing that persistence and willingness to struggle are key. Progress takes effort. The strong encouragement is to watch all the videos and explore the links.
Finally, the lectures introduce the retrospective session concept from software engineering, valuing feedback for future learning.
Exactly. Inviting you, the listener, to start thinking about your own feedback and requests for future sessions or topics. What do you want to know more about?
On a practical note, recommended software is Google Colab web-based, no install needed, and the Python component within Grasshopper.
Right. Accessible starting points.
A specific Colab notebook with basic Python is suggested as a first homework, and the emphasis is on typing the code yourself.
Definitely. To understand syntax, find errors, really internalize it. A structured approach is suggested. Type it exactly, then type by meaning, then independent study.
The lectures also address the potential time commitment, reassuring that initial struggle is normal and necessary.
Yes, building that foundation takes time. Again, the importance of exploring all provided resources, videos, links is reiterated.
We also get a brief overview of the course structure. These lectures are part of lectures, discussions, reviews, assignments, references. Focusing on mandatory sections first is recommended. And the lectures conclude with a strong emphasis on the practical importance of learning to code with the RhinoNet VPI for actual design projects and the final course project.
Yeah, highlighting that this skill set will be incredibly valuable for a wide range of future work in design practice and research. It's a powerful tool.
So as you begin to delve into these resources, keep in mind the core principles: the power of data, the importance of computational thinking, and the essential data structures, pixels, voxels, graphs.
Exactly. Embrace the exploration, experiment. Remember, learning is iterative. And, we're genuinely interested in hearing your thoughts and feedback as you start this journey. What clicks? What's confusing? Let us know.